Welcome back everyone. In today's video, I'll be explaining problem F from the AtCoder Beginner Contest 315. I've provided the correct Python code in the video description, so please look after you've listened to my explanation. Let's start with the problem statement. We have n points on a coordinate plane. They are labeled with numbers from 1 to n. We start with 1 and travel to n, passing through points in ascending order. We are allowed to skip some points, but a penalty will be imposed depending on the number of skipped points. The penalty is given by 2 raised to the power of the number of skipped points minus 1. Our target is to find the minimum sum of the total distance and the penalty, just called cost here, among all the routes from 1 to n. Let's proceed with solving the problem. Our initial key idea is to find the problem a typical dynamic programming question. Why? First, the number of routes from 1 to n is 2 raised to the power of n minus 2. That's because to determine a route, we have an option of passing pi or skipping it for each pi. So this problem can be split into multiple binary choice problems. DP and binary choice problem is very compatible. Plus, we find out that it's not so important to remember the intermediate route. This means that to determine where to go from the current point, you don't remember the information about how you have gotten to the point. These reasons encourage us to try DP. So, we define dp of I as the minimum cost from 1 to I and check the transitions from 1 to n step by step. When you are at point I, you can directly move from I plus 1 to n. So let variable I range from I plus 1 to n. The transition from dp of I to dp of II is given by dp of I plus the distance from I to II plus the penalty up to II. However, here is a problem. We can't determine the penalty value because we don't know how many points we have skipped before reaching I, but we can calculate it if we know the information. Therefore, we need to improve dp to record the number of skipping points. We redefine dp of I and j as the minimum distance from 1 to I with skipping j points. Be careful that it's not the minimum cost, but just the minimum distance. The total cost from 1 to I is computed as dp of I and j plus 2 raised to the power of j minus 1. Then, let a variable II be the next passed point after I, and a variable jj be the number of skipped points up to II. The variable II ranges from I plus 1 to n, but jj can be determined by I, j, and jj as follows. So the transition equation is well defined as follows in this case, and the previous problem has been solved. However, this dp has another problem. That is, the size of dp is too large, and we can't handle it. The variable I ranges up to n, and the variable j also ranges up to n. Since n is at most 10 to the 4th, its size is at most 10 to the 8th. We need further improvement. This is the most difficult part to come up with in the problem. We should pay attention to two facts. First, the penalty function is exponential. The penalty comes to so big if we skip several points. Next, our target is to find the minimum cost. We don't need to think about routes with high costs. What can we say from these considerations? We find out that every route achieving the minimum cost doesn't have so many skipped points. More precisely, we can restrict j, which is the number of skipped points, as j is at most 60. Why? We have the route without skipping points, that is the route passing points from 1 to n step by step. Its cost is roughly computed as a travel distance times n minus 1. From the constraints about coordinates, the distance is at most 10 to the 4th, so the cost is about 10 to the 8th. We don't need to think about routes from 1 to n whose cost is larger than that of the route without skipping points. But here, 2 to the 60th is about 10 to the 18th, so it's large enough to exceed the border cost. Let's summarize the answer. We define dp of I and j as the minimum distance from 1 to I with skipping j points. The variable I ranges from 1 to n, and the variable j ranges from 0 to 60. Let ii be the next state of I, and we only check the value of ii from I plus 1 to I plus 60. Then, jj is defined as previously, and the transition from dp of I and j to dp of ii and jj is given as well. This dp works well because the dp size is n times 60, and the number of transitions per each pair of I and j is about 60. So the total time complexity is about 10 to the 7th, which is acceptable. Finally, when we initialize the dp, we should define dp of 1 and 0 as 0, and everything else as the infinity. With that, I've completed that explanation. If you have any questions about the problem or any requests for solving other ABC problems, please feel free to comment. Thank you for watching this video.